3GPP have big plans to add positioning in cellular systems. 5G positional will act as a natural component in many 5G use cases, such as logistics, smart factories, geofencing, autonomous vehicles, digital twins, augmented and virtual reality. Since use cases are so wide, they also have different performance requirements. For example, application like navigation of robot would need positioning to be very precise as compared to other use cases. Similarly, security requirement can also vary for applications. If we use positioning information to find distance between two autonomous vehicles, we need this information to be derived securely. Due to incorrect distance measurement, vehicle might believe that they are farther than their actual distance. They can speed up and collide into each other, which could lead to the loss of life. Different applications supported by 5G also have different latency, availability, reliability, and scalability requirements. Positioning using enhanced cell ID and assisted GNSS were already introduced by 3GPP in GSM and UMTS, which were the predecessor of LTE and 4G. LTE adopted these techniques, but they were not sufficient to provide localization in indoors and under bad weather. Therefore, LTE introduced observed time difference of arrival estimate that supported downlink-based positioning method. Especially, positioning reference signal was enabled to provide precise localization. This is basically a code with interference suppressing capabilities, which in turn allow for higher level of accuracy and coverage. Along with that, LTE positioning protocol was defined to assist in location services. To satisfy the newer use cases, 5G is now testing other ranging techniques. So far, use of observed time difference of arrival with positioning reference signal is adopted from its predecessor. Although some modifications are proposed to PRS configuration, it is now allowed to use wider bandwidth. It is being tested with beamforming capabilities, and the position in the frame is changed to reduce interference. The new release of 5G standard also introduced sounding reference signal in the uplink. The idea is to use positioning reference signal in the downlink and sounding reference signal in the uplink to enable two-way ranging system. In this work, we have two main contributions. First, we analyze security of 5G NR positioning, especially positioning reference signal, and shows that it is vulnerable to distance manipulation attack. An external attacker can prove that devices measuring distance are closer than their actual distance or they are farther than their actual distance. And since many 5G positioning use cases are security critical, we provide a secure alternative, vRange, which is capable of detecting distance manipulation attack. We will discuss these two contributions in the remaining slides. The positioning reference signal used by 5G NR are basically OFDM symbols, and the symbol duration here is defined by the subcarrier bandwidth and not by the total bandwidth of the system. Therefore, symbol duration or the symbol length is in the order of microsecond. And it is known that the longer symbol lead to multiple distance manipulation attacks, even when data modulated on these symbols is generated cryptographically. For example, an attacker can use early detect late commit attack to perform distance reduction. The aim of attacker is to send symbol earlier than the arrival time of legitimate symbol at the receiver. Since attacker does not know the symbol shape in advance, assuming that the data modulated on these symbols is generated cryptographically, there is a need to do some learning at the attacker's side. So basically, attacker receives part of the legitimate symbol, so the initial part, and uses it to predict remaining part of the symbol, and then commit it in such a way that it arrives earlier than the arrival time of legitimate symbol, and it is being used for time of arrival estimation and the data detection. Since OFDM symbols are long, attacker is basically succeeded in learning the shape of symbol and committing it in advance to perform distance reduction. On the other hand, an attacker can use signal overshadowing attack. The idea here is to replay legitimate signal after a delay delta, which is lower than the symbol duration and with the higher power, such that legitimate signal is hidden behind the attack signal at the receiver. Now this receiver is receiving two overlapping signals, and the legitimate signal have very low power compared to the attack signal. The receiver would use this attack signal for time of arrival estimation and the data detection. And therefore, attacker would succeed in the distance manipulation attack. Both overshadowing and early detect late commit attack are direct attack, where attacker is manipulating the symbol used for ranging. But there also exists the possibility of indirect attacks. For example, an attacker can manipulate carrier frequency offset estimation, which would prevent detection of legitimate signal and in turn will allow acceptance of attack signal for the distance measurement. The possibility of these attacks shows that existing 5G NR positioning methods are not secure, and since many 5G positioning use cases like positioning of autonomous vehicles and access control are security critical, there exists a need for secure alternative. In this part, we present vRange, a design capable of detecting distance manipulation attack we have presented so far. In the vRange, we have made mainly three design choices. First, we reduce the effective symbol duration of the OFDM symbols in order to prevent attacks which were possible due to longer symbol duration. And then we perform signal and data level integrity checks to detect possibility of other attacks. Enabling vRange would not need any changes in the hardware. We only need to do changes at the digital domain. At the transmitter, we need to change the data we are modulating on the OFDM symbols. At the receiver, we need to add module for time of arrival estimation and integrity checks. For any 5G ranging system, the module for time of arrival estimation and validation is necessary. In the OFDM, the data is modulated on the subcarriers, and then inverse Fourier transform is applied to get signal in the time domain, which lead to the longer symbol duration. And since longer symbols are associated with distance manipulation attack, the first change we perform is to reduce the effective symbol duration. In the vRange, we modulate same data on all subcarriers. And when inverse Fourier transform is applied, one sample have energy and everything cancel out each other, so the effective symbol duration is reduced to one sample. Attacker now need to manipulate this sample if he want to perform distance manipulation attacks. In the vRange, effective symbol duration is reduced to one sample. At the receiver, we are interested in finding the arrival time of samples with energy, and we are not interested in finding the whole symbol. Therefore, at the receiver, we search for the arrival time of the samples with energy in them by using the forward search. This design is very useful in differentiating between noise, legitimate, and attack signal, which is critical for achieving accuracy and security in distance measurement. In order to perform sanity of the signals used for time of arrival estimation, we perform signal integrity and data validation check. In the signal integrity check, we check for the variance of the received power of samples arriving at the receiver. The idea is that if two samples are transmitted with the same power and they pass through the same channel, they should have the same received power. Although some variance in their power can occur due to receiver noise, and therefore it should be below a certain threshold. Let's call it V noise. And if variance is higher, then it most probably is an attack. This observation is true only if we can follow two conditions. First, all symbols are transmitted within the coherence time of the channel, which would be few microsecond to millisecond based on the speed at which environment is changing. Second, the delay spread of channel should be lower than the symbol duration. These conditions are met by our design. Now, if we have 16-core modulation to transmit our OFDM symbol, we will transmit our samples with 3 different power levels. If at the receiver we split them into 3 bins based on their transmit power, the variance of each bin should be below threshold V noise in the legitimate scenarios. Data detection is important in these systems, but we cannot trust on 5G's synchronization signal for carrier frequency offset estimation. And since synchronization signal cannot be trusted and there also does not exist approach for secure offset estimation, we are currently using brute force search for offset estimation and therefore data detection. We accept the offset value which provide minimum symbol error rate for the data integrity check in our current implementation. Our receiver design look like this. We use multiple thresholds to differentiate between noise, legitimate, and attack signals. I will now go over the threshold which help us in preventing and detecting distance manipulation attacks. If an attacker wants to perform distance reduction attack, attacker would need to inject symbol earlier than the arrival time of legitimate symbols. Since VRange uses shortened OFDM symbol, it prevents the possibility of early detect late commit attack. The data modulated on these symbols is unknown, and these samples are in the order of few nanosecond, preventing the possibility of learning and committing these symbols. Therefore, distance reduction is possible only if an attacker can guess the data modulated on these samples correctly, therefore reducing the success rate of distance reduction attack. On the other hand, if an attacker wants to perform distance enlargement attack, an attacker would need to prevent detection of legitimate samples at the receiver such that they are discarded as noise. Now, if an attacker would send a copy of legitimate signal after a delay, it would be used for the time of arrival estimation. The first strategy that attacker could use is to reduce the overall received power of the legitimate signal, such that it is discarded during the time of arrival estimation, and in that case, no any integrity check would be applied. Basically, attacker need to perform signal annihilation. But use of shortened OFDM symbol make this task challenging because the effective symbol duration is in the order of nanosecond, and attacker need to synchronize and send the signal, the cancellation signal, in this much time, which is harder to perform. And therefore, an attacker's attempt to perform signal cancellation in general would lead to increase in the power instead of decreasing it. Therefore, reducing overall power of the legitimate signal is not feasible in order to perform distance enlargement. And another approach would be to increase the symbol error rate of the legitimate signal arriving at the receiver without increasing variance. However, satisfying both conditions at the same time is not feasible. An attempt to increase symbol error rate generally results in the increase of variance. Therefore, we can say that collectively, these checks on the shortened OFDM symbol allow us the possibility of detecting distance manipulation attacks. We tested VRange using both sub-gigahertz and millimeter wave setup, and by using appropriate threshold for symbol error rate and variance, we are able to achieve very good performance, and we are able to detect a type of signal manipulation. More results for performance under different channel conditions are provided in the paper. From these results, we can say that VRange can be used as a secure design for 5G positioning. To summarize, many use cases targeted by 5G positioning are security critical. But techniques proposed by the standard so far is not secure. They are vulnerable to distance manipulation attack.